Welcome back. In this video, we are going to solve exercises 1 and 2 of chapter 5. We gave exercise 1 in the final exam of 2015. The purpose is to give an example of a sequence in a normal space that converges weakly but not strongly. So one example would be the sequence Fn of x given equal s sine nx, and this is a sequence of L2 of 0 pi. We have to prove that it does not converge strongly to 0, but it converges weakly to 0. So let us start with the easy part by computing the norm of Fn. The norm of Fn in L2 squared, by definition, is the integral of Fn squared. So it's the integral from 0 to pi of sine squared nx, and you should be able to compute that. We linearize sine squared, so we write sine squared nx as 1 minus cosine to nx over 2. Now, when we integrate cosine to nx from 0 to pi, the result is 0, because we get sine to nx. So get sine 2 and pi minus sine 0, so it's 0. So we just get pi over 2. So this means that the norm L2 of Fn is radical pi over 2. So the norm does not tend to 0. So Fn does not converge strongly or in norm to 0. Okay, now to prove that Fn converges weakly, we split the proof into two parts. We know that Fn converges weakly to 0 if the integral of phi Fn converges to 0 for every phi in the dual of L2 or in L2, because the dual of L2 is isometric to L2. But since we cannot do that directly, we approximate first an element in L2 by a better function, which is a continuously differentiable function with compact support, because we know that the space of continuously differentiable functions with compact support is dense in L2. Why? Because this is actually bigger than the space of CC infinity. Okay, so I mentioned in the course that the space of infinitely many times differentiable functions with compact support is dense in L2, in any LP actually, for P finite. But CC1 is bigger actually, so of course it's dense. And even the space of continuous functions with compact support is also dense because it's bigger. So if the small space is dense, then the bigger space is dense as well. Okay, so first we assume that G is continuously differentiable with compact support on 0 pi, and you have to prove that the integral of G against Fn tends to 0. Okay, this is a sequence of real numbers. So for this we integrate by parts because everything is continuously differentiable. So we integrate sine nx and we differentiate G. So we get G times the antiderivative of sine nx is minus cosine nx over n. So we get G times minus cosine nx over n evaluated between 0 and pi, minus minus, so we get plus 1 over n integral of g prime cosine nx. And now, since g has compact support, then it vanishes at the boundary, as you know. So in particular, g of 0 equals g of pi equals 0, and therefore the term between in brackets is 0. So you just get 1 over n times the integral of g prime cosine. Therefore, when we take the absolute value of this integral is less than the integral of the absolute value. Now, the absolute value of cosine is less than 1, and the integral from 0 to pi of absolute value of g prime, this is of course the norm L1 of g prime. So it's a constant actually. So the absolute value of this term is less than 1 over n times a constant, and therefore it tends to 0 as n tends to infinity. So this proves part B. Okay, now to prove that Fn converges weakly, as we said, we take an element in the dual of L2, or just so a function in L2, phi, and you have to prove that the integral of phi Fn tends to 0. So therefore, as we said, we use the density of CC1. Could have taken actually G and CC infinity if you like, but we don't need, we just need the first derivative of G. We didn't need, in this integration by part, we didn't need further derivatives. So CC1 is enough. Okay, so what does it mean that CC1 of 0 pi is dense in L2? It means that any element in L2 can be approximated by an element in CC1. Okay? This is the content of the density theorem. So it's important. Why? Because the elements in CC1 are better behaved than the elements of L2, are better functions in some sense, they are more regular. Because an element in L2 need not be even continuous. Okay. So this means that given epsilon positive, we can find an element G in CC1 of 0 pi whose distance to phi in L2 is less than epsilon. Okay, and now we evaluate the integral from 0 to pi or over 0 pi. This is just a Lebesgue integral. We write it in this way because Fn and phi are in L2. Okay, so they need not be continuous. So this integral is actually a Lebesgue integral, not a Riemann integral. Here, in this case, we wrote 0 to pi because everything is continuous. So this is just a Riemann integral. Okay, so it's a particular case of the Lebesgue integral. Okay, so we add and subtract Gfn, G times Fn. So we split this term into two integrals, the integral of phi minus G times Fn and the integral of Gfn. Okay, now if you look at the first term and apply the Cauchy-Schwarz inequality, we see that the integral is less than the norm L2 of phi minus G times the norm L2 of Fn. Now the norm of phi minus G is less than epsilon, and this is a constant, as you know. So this is just less than epsilon times the radical of pi over 2. The constant is not really important. So the meaning is that this integral can be made arbitrarily small. Now, if you look at the second integral and you apply part B, because now G is in CC1, the second term tends to 0, so it also can be made less than epsilon if n is large enough. And therefore, when we add together these two terms, we get that the integral of phi of n, an absolute value, is less than a constant times epsilon. Since epsilon was arbitrary, this means for all n large enough, so this precisely means that the integral of phi of n tends to 0. Okay? And once again, the constant is not really important. Okay. So now, if we wanted exactly to have epsilon here, then we would have taken this to be less than epsilon over radical pi over 2 plus 1, but this is not really important. Even if you get 100 or 1000 epsilon, it's the same thing. Okay. So that's it. So this concludes exercise 1. So you should be able to master these techniques. Yeah. So Fn converges weekly to 0 in L2. This is a fundamental example of a weakly convergent sequence which is not strongly convergent. Exercise 2. Another example of a sequence converging weakly but not strongly. So we equip 0, 1 with the Lebesgue measure, okay, as we did in the previous exercise. We don't need to mention this every time. And we consider any p between 1 and infinity. And we consider the sequence of function gn given by gn of x equal n to the power 1 over p times e to the minus nx. Okay, so the purpose is to show that gn converges weakly to 0 but not strongly to 0 in LP. Okay. So let us prove first that gn converges pointwise to 0. The simplest thing is to just take the logarithm. So because gn is positive, so the len of gn of x is len of n to the 1 over p times e minus nx. So since the logarithm takes products into sums, so this is the logarithm of n to the power 1 over p, which is 1 over p ln n, plus the logarithm of e minus nx, which is just minus nx. When we factor by n, we get len of n over pn minus x. And now len of n over n tends to 0, so the term between parentheses tends to minus x. Okay, so it's bounded. And n tends to infinity, so the product tends to minus infinity. If the logarithm tends to minus infinity, it means that what is inside tends to 0 for every x between 0 and 1, of course. So gn tends pointwise to 0. Now, why is it bounded? Just compute the norm LP. So when we compute norms LP, it's better to raised to the power over p in order to get rid of the exponents. So the norm of Gn, the norm Lp of Gn raised to the power p is, by definition, the integral of Gn to the power p. When we raise to the power p, we get n to the 1 over p to the p, so it's n. And e minus nx is just e minus, to the p is e minus n by x. And we know how to integrate that because we have an antiderivative of the exponential. The antiderivative of what is inside is minus e minus n px over p. So we evaluate that between 0 and 1, and we get 1 minus e minus np over p. And since the exponential is positive, this is less than 1 over p. And since p is bigger than 1, it's less than 1. Okay. So Gn is, so when we, now if we want, we can raise to the power 1 over p. So the norm of Gn is also less than 1. Same thing. Okay. So Gn is bounded. Now, second question, we have to prove that Gn converges weakly, but not strongly. So we proceed as in exercise 1, same strategy. Okay, so here we started with proving that Gn converges weakly. So we take an element G, in CC in the space of continuous functions compact supports. We could have taken G in CC infinity, it doesn't matter, but here we don't need the derivative of G, as you shall see. So CC will be enough. So CC of 0, 1 is dense in L2, in LP. Okay, now what does it mean that G has compact support? It means that the support of G is compact, is a compact subset of 0, 1. So it's contained in some compact interval AB, strictly contained in 0, 1. Okay, so in particular, G vanishes at 0 and 1, vanishes at AB actually, if you like. Okay, now if you compute, Gn happens to be C infinity actually, so you can differentiate it. When you differentiate it, this is just a constant. So you get actually, you'll see that when you differentiate Gn, you get something negative actually, because this is a constant, and then you get minus n. So it's minus n times n to the 1 over p e minus nx. So it's negative. And therefore, Gn is decreasing. And therefore, if x is in the closed interval AB, then so x is bigger or equal than a. So Gnx of a is less or equal than Gn of a. And of course, Gn is non-negative. Okay? Strictly positive, actually, because it's an exponential. And Gn of a is by definition n to the 1 over p e minus na. Okay? And yeah, so this yeah, actually this is not true for all and not only for n large enough. Okay. Now we evaluate the integral of g against Gn as we did in exercise 1. So since the support of G is contained in AB, then the integral, so this means that G vanishes outside AB. So the integral from 0 to 1 of this function is also equal to the integral from A to B, because outside AB, G is 0. Okay, so any function vanishes outside its support. And now when you evaluate this by the usual inequality, so the absolute value of the integral is less than the integral of the absolute value. So absolute value of Gx is less than the infinity norm or the supremum norm of G, the maximum norm, if you like. And Gn, the absolute value of Gn is just Gn because Gn is positive, and this is less than, as we said, than n to the 1 over p e minus na. Okay, so it's the integral from a to b of a constant, and therefore this is the integral of b minus a. So b minus a times norm, the supremum norm of G times this quantity. This is a constant, doesn't matter, and this quantity tends to 0, as you know. We proved it actually when we proved that if you don't, so you just take the logarithm as we did. So because the exponential always wins the race, okay? Even so, n to the 1 over p tends to infinity, and the exponential tends to 0, but the exponential tends to 0 much faster. So this is the first step. Okay. Now, if we have taken G to be in CC1, then we could have integrated by parts and get the same result. Okay, it doesn't matter. So now the second part, we take an element in the dual of LP. So it's enough to prove that the integral of phi Gn converges to 0 for every phi in LP prime, because LP prime is isometric to the dual of LP. Now we use density as we did in exercise 1. So given epsilon positive, we can find an element G with compact support and continuous compact support whose distance to phi is less than epsilon in LP prime, of course. And now we do as we did. So we split the integral into two parts: phi minus ggn plus the integral of ggn. Okay, and you have to prove now that each term is less than a constant times epsilon. So same strategy. If you look at the first term and you apply, actually here it's not Cauchy-Schwarz, it's Hölder actually, because it's p. Okay, so the integral of phi minus ggn is less than the norm LP prime of phi minus g times the norm p of gn. So please correct that. This is Hölder. Okay, and since the norm LP of gn by exercise 1 is less than 1, and this is by our choice of g is less than epsilon. So the first term is less than epsilon. The second term, according to the first step, tends to 0, so it's less than epsilon for all n large enough. And therefore, when we add them, we get that the integral of phi gn is less than 2 epsilon for all n large enough. And this means that the integral of phi gn converges to 0, and therefore gn converges weakly to 0 in LP prime. That's it. And yeah, actually I didn't prove that gn does not converge. Yeah. Okay, now, yeah, I didn't write it, but this is something that comes from here. Why gn does not converge strongly to 0? Because its norm is just 1 minus e minus np over p. So when n tends to infinity, the norm tends to 1 over p. Okay, so if you like, the norm LP of gn is 1 over p to the power 1 over p. So it's constant. Okay, so it cannot converge to 0. Okay, so this is another example of, actually it's a family of examples because p is arbitrary. Okay, an example of, concrete example of a sequence converging weakly but not strongly. Okay, so this concludes the first two exercises. The next video I'm going to solve exercise 3 and 4. Thank you for your attention and see you next time.